Hello students, today we'll discuss geodesic polar coordinates. Let's be given a surface S. Of course we're talking about surfaces that are embedded in R3, so the surface is embedded in R3. And the point P on the surface. So I give you a surface and a point on the surface, and now I'm going to fix a given direction in the tangent space. So fix a direction, a vector, call it V, in the tangent space to the surface at the point P. So this of course is the tangent space. Okay, good. And now what I'm going to do is I'm going to write down, I'm going to find a geodesic that goes through P such that the angle that geodesic makes with respect to that fixed direction V is exactly equal to theta, right? So let's let gamma theta r be an arc length parameter geodesic that makes an angle of theta with respect to V. Okay, so that's a lot of words, so let's sort of figure out geometrically what this looks like. So I have some surface. I'm just going to draw some of the parameter charts over here. There's my surface S. Here's a fixed point P on the surface. And then at that point P, I know there's a tangent plane over here, right? And I'm going to write down a direction. So here's my direction V. That direction V is like my initial bearing in polar coordinates, right? When we think about polar coordinates, the angle theta is relative to the x-axis, right? So now I'm fixing a direction because I have to sort of fix a bearing for polar coordinates, and so that bearing is V. And then what we do from this perspective is then I'm going to draw geodesics through that point P that make an angle of theta. So that might be theta 1, for example. Here's another geodesic that makes an angle of theta 2, right? And these are geodesics, and they're, more importantly, they're arc length parameter geodesics, okay? So then that's going to foliate the space, and you can sort of see how we're developing a coordinate system with these geodesics, right? So there's a whole bunch of geodesics, infinite geodesics that traverse through the point P. That's a more abstract theoretical theorem, which we'll prove later. But I'm going to write down all these geodesics that make different angles with respect to this initial bearing vector V, and then that's going to give me my new set of coordinates on the surface. Great. Now, what's one immediate consequence of this? Since the curve is an arc length parameter, what does that mean? That exactly means that gamma dot theta r dot product gamma dot theta r is equal to 1 for all theta, right? And so here, of course, what am I using? I'm using the fact that this dot over here is really d by dr, right? The partial with respect to r, okay? And now, of course, what I can do is I can integrate this relationship, and if I integrate this relationship, this tells me that the integral from 0 up to any fixed r capital of the length of gamma dot theta r squared dr is equal to r capital, okay? That's just a trivial consequence because this expression over here is just constant equal to 1. I integrate 1 from 0 to r, I just get r capital. Great. Now, what I'm going to do is the following. I'm going to also use the fact that this is a product structure, so I'm going to integrate this relationship by parts. So we're going to take this relationship over here and integrate. Well, first thing I'm going to do actually is let me take this equation over here, and I can differentiate it with respect to theta. If I differentiate this equation with respect to theta, since r is fixed, that's going to give me 0. So I'm going to take partial theta of this relationship. If we do so, what we get? We're going to have the integral from 0 up to r of partial squared. And of course, what I'm going to do now is I'm going to make some notation over here. So before we do that, let's make up some notation. So now I'm going to define r geo. So what's r geo? It's a parameterization r geo of r and theta is equal to what? Is equal to gamma theta r, right? And these coordinates are called geodesic polar coordinates. These are geodesic polar coordinates. Okay, excellent. And so now when we take d by d theta of this thing, what we get, I'm going to use this notation now. I'm going to conclude that the integral from 0 up to r of d squared r geo with respect to r and with respect to theta dot d squared d, just a single d, r geo dr is equal to 0. Because when I differentiate this relationship, I'm going to get a what? These are r derivatives already. These dot have r derivatives. And if I do a theta derivative, I'll have a theta derivative over here, a theta derivative over here. So I'm going to have two of them. So really I need a 2 over here, but the 2 is irrelevant, right? I'm just going to leave this relationship. And now I'm going to integrate this by parts. So we're going to integrate this relationship by parts. And this, of course, is a dr over here, right? So I have a dr is equal to 0. Integrate by parts. Okay. If we integrate by parts, what's going to happen? So we're going to have, if I integrate by parts, I'm going to have a partial r geo partial theta dot partial r geo partial r evaluated from 0 to r, right? So we're going to have a partial r geo partial theta r and theta dot partial r geo partial r theta from 0 to r, right? And then, of course, I'm going to have minus the integral of the r squared derivative on this term over here, and I'm just going to throw that on the other side. So this is going to be equal to, since they're equal to 0, this is going to be equal to the integral from 0 to r of partial r geo partial theta dot partial squared r geo partial r squared dr. Okay, beautiful. Now, a couple things are going to vanish. So I'm going to circle the things that are going to vanish. I claim to you that this whole integral over here is just 0. Now, why is this integral over here 0? Well, r is a what? R comes from, this parameterization says that we are gamma theta r, and gamma by assumption is a unit speed or arc length parameter. What? It's a geodesic, right? And so we know that geodesics, the second derivative of geodesics, are parallel to the normal vector of the surface over here. So this thing over here is parallel to n hat, right? And I'm doing the dot product of a tangent vector with the normal vector. So if I dot product the tangent vector with the normal vector, I get 0. So this is going to be 0 over here. Beautiful. And when I plug in 0 over here for r, when we plug in 0 for r, what point are we at? We're at the point P, right? And at the point when r is equal to 0, you're at P. And so there's no change. This partial r partial theta, when r is equal to 0, is always equal to P. So the change in theta over there is 0. As theta is moving around, you're just stuck at the point P. So there's no change in theta over here. So when you plug in 0 to this expression, that turns into a 0. And so what's our conclusion from this? Our conclusion from this is that partial r partial theta, this is partial r geo, dot partial r partial geo, of course, partial r at r capital theta for any fixed r is going to be equal to 0. Beautiful. Okay. What does this tell us? Well, this, of course, is what? That is my f coordinate in the first fundamental form of this surface parameterization. So the f is equal to 0, and what will the e be? The e by assumption is going to be equal to 1 because it's put into arc length parameter. So my first fundamental form for this surface is going to be equal to what? It's going to be equal to dr squared plus some function. I don't know what that function is yet. We're going to study that in further videos. Plus some function g of r and theta d theta squared like that. That's our first fundamental form. Now, why is this first fundamental form great? This first fundamental form is great because when you have a metric or a first fundamental form that has this property, I know what the Gaussian curvature is. The Gaussian curvature is going to be what? It's going to be negative 1 over the square root of g times the second derivative of the square root of g with respect to r, right? So I have a very nice clean formula by the theorem of Regium of how to compute the Gaussian curvature if this function over here, if the metric has this form over here, which we've just proven by this assumption over here, right? Now, one final thing we're going to discuss more broadly in further videos is this curve over here, this special curve. If I look at r geo of a fixed r capital and theta, well, if r capital is fixed, so if this number over here is fixed, okay, if that's fixed, then that gives me a curve. And this curve over here is going to be a what? That's going to be a geodesic circle. So that curve is a geodesic circle. Beautiful. And what characterizes these geometric circles over here? Well, these geometric circles are characterized by the following. Let me just erase something over here. Let's do this. This is what we can't do on the whiteboard, but we can do this on the chalkboard very easily, right? So what I'm going to do is I'm just going to draw one of these geodesic circles. So here's the point P. Then here's a geodesic. Here's a geodesic. Here's a geodesic. Here's a geodesic. They all go through the point P, so those are all geodesics. And if I fix a value of r, what we're going to get is some circle that looks like this. You might say it doesn't look like a circle. But what's the key feature of this geodesic circle? The key feature is that all of these angles over here, I did the best to make them all look like they were perpendicular. All those angles over there are right angles. So this is a geodesic circle. And it always makes right angles. All these angles are right with respect to the geodesics. And all angles relative to the geodesics are right angles, right? And that follows, of course, that's exactly nothing more, nothing less than the fact that this f in the first fundamental form is equal to 0. We're going to see in further videos how to compute the circumference of these geodesic circles, the area inside these geodesic circles, and no surprise is that when I'm computing either the circumference or the area, it will involve the Gaussian curvature. Thank you very much.